And thanks to all the organizers, and I'm very excited for this week. Looks like an exciting program. Yeah, so I'm going to talk about a numerical analysis approach to convex optimization, which I guess means that I'm cheating by talking about continuous approaches to continuous optimization. But I think later this week, Aaron Sidford will talk about how to use some of these algorithms for some discrete optimization. So there will be a connection. Oh, now the slides can skip. So, okay. The thing we want to think about is we have a matrix A with m rows, n columns, and a vector B. And we want to find amongst X that solve an under-constrained linear system, so AX equals B, the one with minimum P norm. Or if you like it better, we can also think about minimizing over X, CX minus D, P norm power P, which now looks like P norm regression. So this may be the more familiar form, but the first one is more convenient. So I'll focus on that one. But the algorithms will be the same. So for P equals 2, this is a linear regression or solving a linear equation. In particular, it's the normal equations, A transpose AX equals A transpose B. And the picture you should have in mind is we have a blue hyperplane of X that solved the linear equation, and then we want the 2-norm ball that's smallest and still contains a point of the hyperplane. So this would be tangent to the hyperplane, and we want that tangent point. And then if you take P equals 1, you get kind of a pointy ball, a 1-norm ball. It looks like this instead, and you want the smallest 1-norm ball that still contains a point of the hyperplane. And P going to infinity gives you this max norm ball, and that's equivalent to general linear programming. And I think it also is with P equals 1. But, oh, and if we look specifically at flow equations, then this problem is maximum flow. Okay, now the focus of this talk is going to be everything in between 2 and infinity. So things like 4. Yeah. But also things approaching 1, but not all the way down to 1. So now you get a ball that's rounder than the pointy balls of infinity and 1, but not as round as the 2-norm ball. Okay, so how hard is it to solve a convex problem? So I take a very different perspective in this talk than Jan did, because I'm going to focus just on counting the number of linear equation solves. And as we just saw, that's really not adequate, because sometimes you can make the linear equation solves very cheap. But we're going to be focused on pushing beyond interior point methods. So for now, we're happy if we can reduce iteration counts without thinking about then making the iterations cheaper. So we can do some kind of axis of difficulty where we have 2-norm regression or linear equations, and infinity norm regression and linear programs. And then in the middle, we have p-norm regression. And then we can plot how many linear equation solves do we need to deal with these things. And then Gauss told us in the 1800s, we can do 1 linear equation solve for 2-norm regression. And Karmakar and Renegar, that work on interior point methods, got infinity norm regression to be problem size. Here I'm not distinguishing between number of constraints, number of variables, square root. Okay. Then Nesterov and Nemirovsky in '94 said, actually, that's kind of pretty much any convex problem that you can do in square root problem size number of iterations. And their perspective on this, to me, kind of feels like what they figured out was how to compile any structured convex problem to hard constraints. But it turns out that you can actually avoid that and kind of get a nice interpolation for the difficulty of p-norm regressions. It's a work of Bubeck et al., where as you approach p being 1, you get down towards just 1 linear equation solve. And then as p goes to infinity, it goes back to the normal square root problem size number of linear equation solves. And they did this by finding a new homotopy that's different than interior point methods. Then we showed that things get weirder than this. At least for now, they look weird. So you can actually get the running time, and this is with Diksha Adil, Sushant Sachdeva, and Richard Peng. You can get the problem size to look like it still approaches 1 for p close to 2, but then it stays below problem size power 1/3 number of linear equation solves until p goes to infinity. Then you kind of, at the very end, we give up. But for any large constant p, it's still below problem size to 1/3. So how does that work? So normally I have kind of a lot of warm-up slides, but I thought we've just been hearing about interior point methods. So I wanted to skip right in and remind us, so how do second order methods normally get us towards our solutions? So interior point methods are an example of this. They use Newton steps to follow this central path. And normally they say, so we have some cost function. We want to improve its value by finding some delta such that x plus delta has lower value. This is the Newton step. And then we make a local upper bound, which is a quadratic function, and a local lower bound. Let me plot. So a local quadratic lower bound that almost matches. And then we choose our update to minimize the upper bound, and then we can see that this converges really fast because the upper bound and the lower bound are really well aligned. And this has a convergence log 1/epsilon. So it's good as a high accuracy method also. But there's a problem here, which is that these bounds are local. And they kind of have to be when we're dealing with interior point methods, because interior point methods blow up to infinity as you approach, like log barriers in interior point methods blow up to infinity as you approach a boundary. So there's no way that you're going to globally approximate your function with a quadratic. Okay, so what we're going to do in order to do much better for LP norms is we're going to find global upper and lower bounds to our functions and use these to take our steps. And we still want to choose a delta that minimizes the upper bound. But now the upper and lower bounds are going to be well aligned, and we get this log 1/epsilon convergence rate, but we don't get the same dimensional dependence that we had before in interior point methods, because we're now actually using global approximations. Okay, but where interior point methods converge in square root m log 1/epsilon iterations to this much error. Can we see this in? Okay, so let me just say it again for the ones on Zoom. Square root m log 1/epsilon iterations. We just need to take roughly log 1/epsilon iterations of steps like this, but that seems too good to be true, right? So these steps have to be hard to take. So what makes these envelopes, this upper and lower bound, tractable to take steps with regards to? So the first thing that's important is that we get a very nice notion of constant approximation being sufficient to make progress. So where instead of trying to solve a p-norm approximation problem to high accuracy, we now convert it into a progress step with respect to this upper bound, which only has to be solved to constant accuracy. So now we have an easier problem, and that opens up, and this is really a key point, so we'll go into it more, but this opens up now for using sort of different families of algorithms that are not so good at getting high accuracy solutions to things, but maybe will be faster than interior point methods. So now it's enough to do, say, if we solve each of these update problems to constant accuracy, we'll lose a constant factor here, and it's actually going to depend on the p. So let's write O1 p, this many iterations, if we only solve each update problem to constant accuracy. Okay, so why can we find these constant approximate delta? So the ingredients of our whole algorithm is just going to be come up with these envelopes and then use a multiplicative weight method to find steps that minimize this upper bound. And now the key point that this sort of switch to a very different kind of algorithm achieved is these multiplicative weight methods turn out to allow for a notion of acceleration, which we don't have in interior point methods. And this really somehow is related, and we don't understand this very well yet, but it's definitely somehow related to acceleration in the sense of Nesterov. Okay, so, but before we get into that algorithm, let's talk more about what these envelopes look like, these upper and lower bounds. So we have p norm power p. That's just a sum of the coordinates power p. And then with p equals 4 and 1 coordinate, let's just try to understand what the upper bounds and lower bounds look like. So we switch from a value of xi to the 4 to our new updated value of xi plus delta I power 4. And then we can just expand out all the terms. And then we start to look at each of them. So if we wanted to do a Taylor series approximation of this function, we would have the linear, the constant term with respect to delta and the linear term with respect to delta. That would be our linear approximation. Now, if we take in the quadratic terms as well, we get the curvature right. And then quite clearly, if we take delta to be very large, the behavior of the function will be governed by the last term. And it turns out just taking these terms is enough to give a global approximation, but this has somehow crucially simplified the problem. So now we have that this linear plus local curvature plus long range behavior with the nonlinear part scaled down a bit sits below the true value. And with the nonlinear part scaled up a bit sits above. So this is our upper bound and lower bound. Okay, and just to convince you that this should be true from my picture, here's the difference between 1 plus delta to the 4 and its linear approximation. Now, clearly, if I look far away from 0, then I have a 4th power behavior. If I zoom in, just by Taylor series, but also by the calculations we saw before, this has to be locally quadratic because we subtracted out the Taylor series. And now the question is just how wrong do we get it in the middle? But all we're talking about is one coordinate. So like we just need to understand how we get this one coordinate wrong, and it can't depend on anything except p. So there has to be a constant factor in p that gets this right. And so the idea is going to be, we say that the difference between the actual function value and the linear approximation has to be roughly up to some constant that depends on p, delta squared plus delta power 4, here in the power 4 case. Okay, so now this lets us do what we call iterative refinement using these updates. And so I just want to plot out what is the whole of the algorithm. So we start with the original problem that we want to solve. Then we create an update problem, which is now asking us to find delta, the change to the function value solution, that now is supposed to minimize this function that looks like linear plus quadratic plus power p, subject to a constraint that in order for x plus delta to satisfy the linear equation, we need a delta equals 0. Then we're going to solve this with this multiplicative weight method that has acceleration or width reduction. So the way I can actually formally understand this is it's width reduction, but I like to point out that it is in some sense also acceleration, even though I don't have a good handle on what that sense is yet. That gives us a constant factor approximate solution over here. And notice that when I say constant factor, I really mean to this thing, and I drop the constant term in the function. There's no constant term here. There's a linear, like really, like if I put this to 0 with respect to delta, I get 0 value. So if I recover a constant approximation to this, I'm really getting a constant factor of the progress that I could make. And this is why we get this really fast convergence. Okay, and then now I revealed what is the p dependence. I make a 1 minus 1 over 2 to the p factor progress by this. Okay.
Right. So just to clarify, you are getting like multiplicative progress in the gap, basically.
Yeah, multiplicative progress in the gap. That's, thank you, what I was trying to say. Okay, and now we have time to go into more detail, but I want to mention there's been a lot of follow-up work since. So very recently, Adil, who was one of the co-authors on this paper, and some et al.'s, which I think is Sushant Sachdeva and Brian Bollins, worked out how to make this approach work to optimize what they call quasi-self-concordant functions. So it should be pretty clear from the pictures that we saw that it would be weird if this method was somehow stuck with only doing p-norms, right? We were sort of reasoning a little bit about its local behavior and its long-range behavior of some function in order to construct upper and lower bounds. And it seems like that shouldn't just get stuck at p-norms, right? And that's what they then carried out. Then we had a paper on using this to do unit capacity p-norm flow in number of edges power 1 plus little o1 time. And this is what Aaron Sidford and Yang Lu relied on, I guess also Tarun Kathuria, in order to get unit capacity maximum flow by doing an interior point method whose steps use this algorithm. And then they got maximum flow in unit capacities, number of edges power 4/3 plus little o1 time. And questions?
Yeah, maybe you could repeat this one. But I'm a little confused by the dependence on p.
Yeah.
1 minus 1 over 2 to p. That's sort of nasty. That never was set to 2 to the p log epsilon.
Yes, it is nasty. Now, it has already been somewhat improved this is another paper by Diksha Adil and Sushant Sachdeva. They bring it down to p log 1 over epsilon iterations. That's a lot better. But the thing is that sort of for us, this didn't really, I mean, it's nice, but notice that if I want to take my p-norm to be an approximation of an infinity norm, then I need p to be about log n over epsilon. So this actually does give like a nice avenue for doing infinity norm approximate algorithms with a 1 over epsilon approximation. But it doesn't really kind of let us get high accuracy things for infinity norms. So this kind of changes especially maybe in practice, what sort of large P you can deal with, but sort of in theory, we're still far from getting a high accuracy algorithm for infinity norms via just this approach. And I want to highlight, because we have, you know, we're a workshop, we should be working on things, that there are some nice open problems. So we have p-norm flow in number of edges power 1 plus little 1 time. It's be exciting. Maybe be careful with that one. There could be people working on it already. And the big difference here is this is unit capacity, right? And that's, we're really kind of, it's a nice algorithm, but it uses a big hack to work. And that hack does not exist once you go away from unit capacities. So can you make like it would have to be a more natural approach in order to remove the capacity restriction? Can you get maximum flow to go faster? And also, does this stuff exist for linear programming? This is not clear at all, I think. So these accelerations.
Just to be clear, with the new p log 1 over epsilon,
Yeah.
So that why doesn't that work for higher accuracy for infinity?
Because you get a running time, like a number of iterations that look like log n log 1 over epsilon divided by epsilon. So you have an epsilon dependence. So whereas to me, a high accuracy algorithm has a log 1 over epsilon dependence.
Makes sense. Thanks.
And I don't have good answers here, right? This I really don't know, but maybe, yeah, I guess Aaron will talk about this. So there are some ways to get some acceleration in some interior point methods. That's what's going on in this paper. Okay, so we have more time, either more questions or I can continue into more details about some things. I'll keep going. Oh, but I had a thank you here, just in case we ran out of time, for Diksha and Richard and Sushant, and Di Wang was on the p-norm flow paper. So how do we use these multiplicative weight methods to take a step? I just want to talk briefly about it. So we want to get a constant accuracy solve of this upper bound thing via n to the 1/3 linear equation solves. And there is a simpler case of this that was already done, which is Cristiano Keller, Madri Spielman Teng figured out how to do a constant accuracy solve of maximum flow via n to the 1/3 linear equation solves, or really number of edges linear equation solves. I think we want to not dwell too much on the algebra, but just to say it briefly, so for those who know some multiplicative weights, think about taking maximum flow and scale it such that the optimal flow has norm 1. Now, what a multiplicative weight algorithm wants is an oracle that does something like this. Given some probabilities, so summing to 1 for each edge, return a feasible flow with respect to the demands such that the average entry is at most 1 plus epsilon in order to get a 1 plus epsilon approximate solution. And then the worst case, how large can any particular entry be, should be bounded in something that's what's called the width of the oracle. And this will govern the running time of the algorithm. And then using multiplicative weights, you can get to an epsilon approximate solution by averaging together flows like this. And you need rho epsilon power minus 2 log n calls to the oracle. And I think maybe one would think it should be rho squared somehow. But it turns out that the right number is rho here. So for sort of, you can have multiplicative weight methods that get a rho dependence in some settings. Okay, and then what is the oracle? The starter oracle, not the one that gets acceleration, is that you take an electrical flow with respect to these probabilities plus a little bit of a regularizer just so it can't go all the way down to nothing. And that regularizer will help make sure that no edge has too much flow on it. And then you just calculate and you get that this has good average behavior and the maximum entry is at most square root n over epsilon. Okay, but when is the oracle bad? And now this is a picture about flow, but it turns out all of these things have analogies for general regression. So we can do the same ideas for p-norm regression. So you have a graph that looks like this. You want to send from the top node k plus 1 units of flow to the bottom node. And a max norm flow would spread this evenly across one path here and k paths over here. And then you would have 1 unit on everything. Okay. But the L2 minimizer will put it from its perspective, having one edge at length 1 is the same as having k edges at length k. So it's going to send half the flow on one edge. And that means that you have that both the 2 norm and the infinity norm are about k. And so you get a width of k, and this graph has about k squared edges. So that's a square root number of square root problem size width. So this would give us the same as interior point methods get, like a square root n or m number of steps. Okay, so here is an easy fix. This is the observation by Cristiano et al. Just remove the bad edge. This makes the L2 minimizer look a lot more like the L infinity minimizer. So if there is what is the oracle now is you try and see what you get. If there is an edge with too much flow on it, then you delete it and you try again. And then turns out there's quite a bit of weight to make the work that goes into making this work for p-norm regression, but it's just kind of translating this into general geometry. And it turns out that then as you look at p close to 2, you can't just delete large edges anymore. Then it becomes a little bit more subtle what you have to do, but it's you look at edges with too much flow on them, and then you adjust the cost of using them up in some sense. So we solve this to constant accuracy. Now using n power 1/3 linear equation solves in n by n, roughly n by n problem, for example. So now I just want to show you where does the 1/3 come from, but I don't want to do it as an upper bound because that's a little bit harder to explain. Instead, I'll show a lower bound that matches. So for this procedure, at least, of deleting edges. So we want to send k plus 1 units of flow in and take k plus 1 units out in this graph, which has, one path of length 1, k paths of length k, and then it recurses with its through here with a one smaller parameter. And what you need to do here for a max flow is send 1 unit on every single edge in the graph. But your electrical flow will not notice the recursion at all. It's just going to send half the flow on this one path and then half the flow on these k paths of length k, and then repeat the same and only notice one level of the graph. And then you delete one edge. And now you try again with a new electrical flow. So you delete the 2 bad edges. Now you discover one more level in the graph. Then you discover one more level. And this graph has k levels. So each time you need to copy the graph with a parameter 1 smaller because you sent, or 2 smaller, you sent some of the flow going this way. So you end up needing k deletions, and the graph has size roughly k cubed. And this is roughly where the n to the 1/3 is coming from. And then let me just mention, I don't have a slide about this, unfortunately. I forgot to put it in, I can see. But there are these papers on higher order acceleration. So which ask, if I do I have a function that's smooth in some sense. Then I do a high order Taylor expansion of it. Then I take a step with respect to the high order Taylor expansion. Nobody knows how to take that step yet, but you could suppose that you could. And then you get some convergence rate for a high order gradient-based method. If you kind of heuristically translate these algorithms, which are not complete algorithms yet, into our setting, it looks like they get exactly the same running time. So we don't know how to make them complete algorithms yet, but they seem to be getting the same running time at every single p. And there's this very interesting thing that in that oracle model, there is a matching lower bound. So it's possible that this dependence on iteration counts that we get for any p is optimal. I don't know if this is true, but if you believe that translating these algorithms to this regression setting that the translation that we would suggest is optimal, then you get this weird phenomenon that maybe these iteration counts are actually optimal at every peak, essentially. That's it. Oh, and I should say that observation is due to Brian Boland's, but I can point you to it offline. Okay, thank you.